Okay, so let's take a look at how convex functions may help us. So our proposition 1 would be a very important thing, saying that we now may guarantee global optimality when we are talking about convex functions. So what's that? It says that if we have a convex function f over a convex domain capital F, then a local minimum would be a global minimum. Okay? So somehow we need two conditions. We need to have the function to be convex, okay? And also the domain, or you may consider that as a feasible region, needs also to be convex, okay? So graphically, let's take a look. What does that mean? So basically, when you have some figure like this, okay? If you have a figure like this, then pretty much you can say, oh well, if we are talking about a region like this, then local mean would be global mean, alright? Because graphically it looks like this. But of course, if you expand your feasible region to this part, then in that case, a local mean, okay, a local mean here is actually not a global mean, alright? So because the function is not convex in general, so a local mean does not mean a global mean. But if you are talking about another function at the right hand side, alright, this is precisely and correctly a beautiful convex function. So if you are talking about the feasible region here, then pretty much the local mean here is the only local mean, which is also a global mean. Alright? So when we are talking about convex functions over a convex domain, then a local mean would be a global mean. So very similarly, if we are talking about a concave function over a convex domain, then a local maximum would be a global maximum, because your function look like this, right? So a local maximum would be a global maximum because your function cannot be look like this, all right? So that's pretty much the idea. So this proposition is so important that we need to prove that to you. So let's say this is not the case. Let's say this is not true. So let's say a local minimum x prime is not a global minimum. So that means there exists another solution that is better, right? For minimization, that means the objective value is even more smaller. So the graph may be look like this. You say there is a local minimum, but at the same time there is another one that is better. So that's a global minimum. So consider a small enough lambda such that we are using lambda to combine the second point and the first point to get to your x bar. Okay? So in this case, we are doing some kind of convex combination, right? And in particular, we are using a small lambda. If you consider, well, small lambda as something like 0.1, then the second point only gets 10% of the share of your new solution. So your new solution is going to be closer to your first point. So that's why on the visualization, your x bar is here. All right. So in this case, let's say your f of x bar is greater than f of x prime. Why would we say that? Because we know x prime is a local mean. So if you have a point x bar that is very close to x prime, you would see that this point is greater than that because x prime is the local mean. Okay, so such x bar must exist because x prime is the local mean. Now consider the following. Let's say, okay, I now want to consider f of x bar. So f of x bar is the height here, alright? And that's going to be equal to f of this linear combination, or I should say convex combination, because this and that is definition. Okay, and then we all know that this point is greater than or equal to f of x prime, as we mentioned about the fact that x prime is the local mean. And then if we want, we may split f of x prime to lambda times f of x prime plus 1 minus lambda times f of x prime. Okay? And then we also know that this guy, f of x prime prime, is even lower. So after all this definition, the derivation, what do we have? What we have is that we are getting a condition violating the fact that f of x is convex. So we have one part here. We have another part here. We see that when we connect 2 points, the line segment, okay, the line segment here does not lie completely below the above your functional points. Okay, so when we are talking about this line segment, the way to obtain this line segment is to first get the height, second get the height, and then do linear combination. Okay, so the line segment pretty much is the last item we have. However, if we get these 2 points and then we get its linear combination first and then plug in, that's something we have here. So this is a particular example showing you that your function point is greater than or equal to your line segment. This violates our assumption that the function is convex. So the function cannot be convex. If you want to have all the things true, your function cannot be convex. That's a contradiction, and thus the local mean x prime can have no other possibilities. It must be global mean. So one thing I want to remind you is that for proposition 1, the convexity of the feasible region is actually required. So maybe you may consider this example. Let's say I want to minimize x1 plus 2 to the square plus x2 plus 1 square. Okay, so if I want to do that, then pretty much I'm talking about some kind of convex function. All right, so this is convex because again this is a ball, and the curvature is upwards. So pretty much this is something we understand. Okay, let's say there are 2 constraints. The 2 constraints are first x1 squared plus x2 squared must be less than or equal to 9. So that's one thing. So pretty much we are talking about this circle, okay? And also we say either we want x1 to be greater than or equal to 0, or x2 should be greater than or equal to 0. So it would be weird for you to see or, because typically we don't do that when we are talking about a typical mathematical program, right? But in this particular example, if this is really the case, you are going to have your feasible region here. And once you do that, you're going to see that for this objective function, our optimal solution is to have x1 to be minus 1 and x2 to be also x1 to be minus 2 and x2 to be minus 1. All right, so it's here. And then let's see that we have one local minimum, which is at 0, negative 1, because at this point, pretty much you don't have any other nearby point that is better than that. So this guy is 0, negative 1 is local mean. However, a global mean is actually negative 2, 0. Right? It's here, it's even closer. So all the example here just want to show you one thing. If you want to make sure that a local mean is a global mean, you need the function to be convex. Okay, this function is convex. And you need your feasible region also to be convex. When you have only one of them, you cannot guarantee that your local mean is a global mean. So we also have proposition 2, which is not so important but also very interesting. It talks about the extreme point idea. So now we know if we are minimizing a convex function over a convex feasible region, a local mean is a global mean. What will happen if we try to minimize a concave function? Well, a concave function pretty much look like this, right? So when we want to minimize it, we know the optimal solution is either at the left-hand side or at the right-hand side. So one may go down on a concave function if we move toward the boundary, and this gives us the following condition. It says that if we are talking about a convex function minimization, if that function has a global minimum over a convex feasible region, then we would have a global minimum that is an extreme point. Okay? So this somehow answers our original two questions or the two difficult points we mentioned. We want local mean to be global mean. If that's the case, we need to minimize a convex function over a convex set. Or sometimes we want extreme point optimal solutions, then we need to have to minimize a concave function over a convex set. So as long as we are talking about convex function, concave function, convex sets, we actually have these two important propositions, and that's going to help us guarantee the effectiveness of our algorithms.